All right, so as Maria said, I'm Miles Timpe. I'm a planetary scientist, so we're going to go back down in scale now. And this is a mistake you should never make as a computational scientist, which is to go after all of the cosmological people, because I'll say multiple times in this talk that my simulations were expensive, and you guys are going to laugh because 100,000 computer hours for us is a lot, and 30 million is something that would be nice, but you never hit that with planets. So what I'm going to talk about is essentially how we can replace simulations of collisions between planets with various methods from machine learning. But first, I want to basically motivate to you why we should care about collisions between planets. And you might be aware, for example, of the idea that the moon was formed by what's called a giant impact, but also Mercury's large core is one of the things that we think might be explained by a giant impact. It has a core that's much larger than the other ones in the solar system. Like I said, the origin of the moon, which is a problem I'm working on now with my professor Ben Moore. The Martian hemispheric dichotomy, which is essentially the idea that an impact created the difference between the northern and southern hemispheres on Mars. Another one is Jupiter's fuzzy core, which is also work done by my colleagues at University of Zurich, Ravit Haled. And this is the idea that Jupiter has not a solid core, but essentially a fuzzy core as the result of an impact. Another one is Uranus's tilted axis. So Uranus rotates essentially at near 90 degrees. And as a short aside here, since this isn't an astrophysical talk, I should tell people that are not astrophysicists that if you ever do work on Uranus, you're never going to get a good press release ever, or a serious one at least. So there was a recent study done on a giant impact on Uranus and how it got its tilt. And this was done by a PhD, Jacob Kegereis, who's at Durham University, and this is some really cool work, and he published last year, and I highly recommend checking this out. And another one here is the ice giant dichotomy. So we know that Uranus and Neptune should be very similar, but they do have differences that we see in the heat flux from the planets, and we think this is also due to one of them being impacted by something very large. Also, the origin of the Pluto-Charon binary system is something we think might have formed as a result of an impact. But I'm not so interested in each individual collision. What I'm actually interested in is planet formation. And so generally what we have is something where you start with a big gas, or disk of gas and dust, and these little pebbles form into larger and larger rocks, and they start to collide together and grow. And so what you see here is essentially a number of n-body simulations. So these are all little particles orbiting the sun, and all of these are the exact same initial condition, or within 1 millimeter. And if I run this, what you'll see is that they all suddenly have very different outcomes. And so this is to say that when we're dealing with collisions in planet formation, you can never just run one scenario. So this problem with having to simulate collisions is amplified by a factor of 100 because you have to do a lot of realizations of each planet formation scenario. And so what you see here is basically what happens when two of these particles come within some distance of each other. You basically conserve mass and momentum, and they become one particle. And this is what's known as perfectly inelastic merging, and it's what's been used in almost every single planet formation scenario to date. And so why do we want to solve this with machine learning? So basically the idea is that these are very important physical processes for planet formation and also for these questions about individual planets in the solar system. But these simulations are relatively expensive for a planetary scientist. And the parameter space is very high dimensional, so you have to take into account the core mass fraction of the bodies, their orientations, rotation rates, temperatures, and all of this kind of thing. And all of this can affect the outcome of the collisions. Also, so we've had, like I said, you have this perfectly inelastic merging, which is just merging the bodies together, and this is really not getting the job done. A number of semi-analytic approaches based on smaller data sets have been tried, but they're also not very good, and I'll show that in some stuff soon. Also, yeah, okay, Maria's going to keep me on time. I'm notoriously going way over my talk time, so by force if necessary. The other thing we need to do is we want to be able to generalize this to any kind of output property of these collisions that we might be interested in. Right now, the semi-analytic and analytic methods, this is something you can only really get the mass and the velocities out, maybe the core mass fractions if you make some simplifying assumptions. But they're not very generalizable beyond that. And so what we want to do is look at a lot of different stuff like their core mass fractions, their rotation rates after the impact, their heat fluxes, and any number of things you might be interested in, like magma ocean depth and stuff like this. And also, one of the most important aspects of this in the long term is that we want to actually be able to put these models, these machine learning models, into n-body simulations, so they can be used in what's being termed on the fly. And they should also provide us with physical insights, and sure, it would be nice if they actually obeyed physics. And so how did we do this? Okay, so for the data set, we simulated a new set of 10,700 collisions. This is using smooth particle hydrodynamics on the supercomputer down in Lugano at the Swiss National Supercomputing Center. And this required approximately 100,000 computer hours, which was very expensive for us. And we did this using something that Misha mentioned, which is Latin hypercube sampling. And I'll explain that in the next slide. And we generated 3 sets, all of these being a Latin hypercube sample with the same parameter ranges. So we generated one with 10,000 collisions, one with 500, and one with 200. The one with 200 I won't talk about, we just use it for convergence studies. 500 was basically our validation test set, and then the 10,000 was our training data set. And all of these simulations are now or will be available this week on the Dryad repository at this DOI, publicly available. And then quickly, the Latin hypercube sampling is essentially something that allows you to avoid taking like a uniform grid sample. Because the problem for us is that if we wanted a relatively low resolution in the dimensions, these 12 dimensions, we would have to simulate 10 to the 12 collisions. And this is 8 orders of magnitude beyond what we could potentially do with current computing resources. So we've taken this Latin hypercube sampling, which you can see here, and this essentially just makes sure that you can break up the space into a bunch of columns and rows, but in much higher dimensions. And you only have 1 point per grid row, like column and row. So this is just basically what our simulations look like, if you make them into kind of a nice, smoothed thing. But these are just 16, but you can see basically if you go up here, these are like higher velocity impacts as you go up. This is more of like a grazing impact. This is a head-on impact. And you can see generally what happens is that like here, you tend to destroy the whole thing. It's very small, I know. And down here, you tend to kind of merge and just get a little bit of gas that's coming out. And in reality, when we're actually like dealing with this and we're looking at the outcomes of the simulation, this is the Lagrangian method with particles. You can't really see, but what happens is that you get out like in a hit and run collision scenario, something like this with 2 bodies. So this is the second largest remnant, and a bunch of debris. And we want to basically say, what's the mass of this? What's the mass of this one? What's kind of like the spatial distribution of the debris? What are the rotation rates, core mass fractions, iron fractions, and this kind of thing. And how am I doing on time? 2 minutes? Okay. All right, we're gonna go fast. So basically what we did is we took all of these output parameters that from this one here, we took maybe 100 output parameters that are of interest to us in terrestrial planet formation. We took a subset of those parameters that we were interested in that we might want to put in n-body simulations, and we ran convergence studies on these. So this is logarithmic on the axes, up to 100%. This is about 1%. And these are the last 50 collision timescale, like you can call it the last 50 steps of the simulation, or last half of the simulations. And so the interesting thing is what you want is you want to essentially see that these have converged to below 1% to use them, but in some cases, these haven't. So up here, you see that the radii and rotation rates have not converged. And this is actually a physical process because you have conservation of angular momentum and these things are heating up and expanding. But that's just to say that they're not really good for use in emulation because they're still having these ongoing physical processes. All right, and so what we used as our data-driven methods for machine learning and uncertainty quantification is polynomial chaos expansion. This is what Misha just talked about, so I fortunately don't have to explain this again. And Gaussian processes we also used, which is a function-based kind of data-driven method. And then we used neural networks, but just more simple multi-layer perceptrons with about up to 3 layers, 24 neurons in each layer. And then we used tree-based methods, so XGBoost. And then, of course, we compared this to all the previous analytic and semi-analytic methods, which are just a method from the Japanese group and one from a group in the UK. And our training pipeline is essentially, for every post-impact parameter, we test all 4 of these methods. We train on the 10K data set. We do hyperparameter optimization with HyperOpt, or UQLab in the case of PCE. And we do an 80-20 train test split, 5-fold cross-validation, and then validate on this set of 500. And then we do the sensitivity analysis with Sobol indices from PCE, which Misha already discussed. And so I just have 2 slides left. And the results are basically this. This is our prediction. So this is what we get out of the simulations on the x-axis here. This is the predicted values. So if you had a perfect predictor, it would lie along this line here. These are the 3 semi-analytic methods: PIM, impact erosion model, EDACM, which no one knows what it stands for. It's impossible to find out. PCE, GP, or Gaussian processes, XGBoost, and MLP. And you can see that the previous methods are not very good. And they're limited to basically these things here. It's just they can't predict these because you can't make a semi-analytic model for this. But all of these tend to do extremely well, and they all tend to do well within the expected variance. So you can't really distinguish any best data-driven model. You can only say that all of them work extremely well. And so if we look at this feature sensitivity, I've knocked this on its side because it's a bit too tall for this, but you can see here that there's a very clear set of pre-impact parameters that tend to determine all of the post-impact parameters, which is shown here. And this is essentially the impact geometry and velocity, so kind of the energy that goes into the impact. In some cases, you can see there's ones that are like very clear that are not part of this. And this is basically the obliquity, so how far something is tipped over on its side of the remnant, the largest remnant that comes out. And it's determined almost entirely by the obliquity of the largest body coming in. So basically what you put in, you get out. We also looked at data set requirements, and we just saw that about 1,000 collisions is all it takes to get to about your margin or your optimal accuracy, with only marginal gains thereafter. And these are different scales. So basically for some parameters it's really easy, and other parameters it's really hard. I'll just say really quickly that the work to be done is that we'd like to put in physical self-consistency. So these models will more or less obey conservation laws of like angular momentum and mass. And then with that, I'll say thanks. This paper is going up tomorrow morning on the archive, Planetary Science or something like this. And then the simulations are all available on Dryad sometime this week after they've been curated. And then my co-authors, Maria, Misha, and Joachim and Stefano, who are also in Zurich. And that's it.